We're going to look at another example. In this example, I have got hydrogen peroxide, which is H2O2, and it is becoming water and oxygen. And if I draw this out, and this will be drawn for you, you're not expected to know the structure of H2O2, but H2O2 is a hydrogen bonded to an oxygen, bonded to an oxygen, bonded to another hydrogen. So there's your H2 and your O2, and this is the way the atoms bond together. Okay, and that hydrogen peroxide is going to become water, which is a HOH, and you're getting oxygen, O2. Now, oxygen has a double bond between the two oxygen atoms, not just a single bond. But again, this will be drawn for you. You'll get to see your bonds. Now, in this equation, we've had to use big numbers to balance the equation. I've got a big number 2 here in front of hydrogen peroxide and a big number 2 here in front of the water. And what those big numbers mean is that I have got 2 molecules of hydrogen peroxide. So I don't just have one of them, I have got 2 of them. I'm going to draw a second. And here I've got 2 molecules of water, so I'm going to draw a second molecule of water. But here, I've got no number in front of the O2. That tells me I've only got one O2 molecule. So when I'm breaking my bonds, I'm not just looking at the bonds I'm breaking in one molecule of H2O2. I'm looking at the bonds I'm breaking in 2 molecules of H2O2. So when I'm doing my bond breaking on the left, I can see that I have got 1, 2, 3, 4 oxygen-hydrogen bonds to break. And I have got 1, 2 oxygen-oxygen bonds to break. And on the other side, I'm looking at the new bonds that I am making. And I can see I have got 1, 2, 3, 4 oxygen-hydrogen bonds to make. And I've got 1 oxygen double bond oxygen to make. And to get the values, you'll always be given a table. So in this example, I've got my table here. I take these values from my table and I plug them in so that I can do my calculation. And when I do that, I calculate a value of 2148 kilojoules for the energy required to break the bonds. And I calculate a value of 2354 kilojoules for the energy that's released from all the new bonds that I have formed. And when I want to calculate my overall energy change, it's going to be the reactants minus the products. The reactants, 2148, the products, 2354, and you end up with a value of minus 206 kilojoules of energy. Again, that minus is telling me that my reaction is exothermic. Okay, more energy is being released from the bond making than you are putting in to break the bonds. Overall energy is being released, therefore you get a negative value when you use this equation. The reaction is exothermic. I'm going to get you to do a few for yourself. So if you go to your booklet, so I've done worked examples for those 2 that I've just gone through in the video, they're in the booklet. If you go to the practice questions and start with question 6. So I've given you a table of all of the different bond types with the bond energies that you need, okay? And you'll use that table to answer question 6 down as far as 13. So don't do 13, do 6 down to 13 by yourself and then come back here for the answers. Just a note on the table in question 12. So what I've done is I've given you molecules and I've drawn them out for you so you can see what bonds you need to break. And it asks you in the first column for the energy required to break all the bonds. So you use your table up here. So for example, the first one, you're breaking a hydrogen-hydrogen bond. You look at your table and you see that a hydrogen-hydrogen bond is 436 kilojoules of energy. The last column, it asks you for the energy released, okay? The energy required to break the bonds is going to be exactly the same as the energy released when the bonds are made. So the answers that you've got here are going to match the answers that you've got here the whole way down. Okay, the point is just to emphasize that the energy required to break a specific bond is exactly the same as the energy released when that bond is made. So have a go with question 6 down as far as 13, press pause, and then come back when you are finished. Okay, so if we look up the answers, remember using the table above, CH bond, it's 413, If it has 4 CH bonds, then it's 4 times 413, 1652 is your answer. 3 CH bonds is going to be 3 times 413 plus the value for a CCl bond, which is 346, and that gives you an answer of 1585. Then you're doing 1 CH bond and 3 CCl bonds. You should get 1451. Hydrogen chloride, you're breaking a hydrogen chlorine bond. The answer is 432 to break it. It's also 432 to make that bond. Okay, so all of these values I'm getting from this table here. Okay, you're just taking the values from the table and multiplying or adding them to get your answer. Actual table here, I'm just going to leave it up. Okay, so these answers should be the same on both sides. The first few should hopefully be straightforward. Down here in CO2, you've got 2 carbon double bond oxygen, so it's 2 times 799. Here I've got 1, 2 carbon-carbon bonds, and I've got 1, 2, 3, 4, 5, 6, 7, 8 carbon-hydrogen bonds. When you do all that out, you get 3998. Here I've got 1 carbon double bond carbon, and I've got 1, 2, 3, 4 carbon-hydrogen bonds. That gives you 2266. Here I've got 1 carbon-carbon bond to break, and I've got 1, 2, 3, 4, 5, 6 carbon-hydrogen bonds. The alcohol here, I've got 1 carbon-carbon bond, 1 carbon-oxygen bond, 1 oxygen-hydrogen bond, and then 1, 2, 3, 4, 5 carbon-hydrogen bonds. So quite a lot of bonds for breaking and making. I get 3, 2, 3, 4. If you had problems with that table, message me and let me know. But you're just using the values from above, counting the number of bonds that you've got, and working out the energy required to break those bonds. The energy to make those bonds will be exactly the same. So in this table, I'm just looking at individual molecules. How much energy would it require to break that molecule apart? How much energy would it require to put that energy back together? But in question 13, 14, 15, and 16, I've given you chemical reactions. So this is similar to what I was doing for you earlier on in the video. You've got reactants on your left. You need to calculate how much energy is required to break those bonds on the left. And then on the right, how much energy is required to make those bonds. Now, the way I've written it out for you here, I haven't drawn the structures, which makes things a lot harder. I'm going to draw the structures for you on paper so you can see how they're drawn, and then you can use the values in the table above to calculate your energy changes. I've given you the answers, so you'll know straight away if you are right or wrong by comparing your answer with mine. If you want a real challenge, then try and draw these molecules for yourself and see if you end up getting the right answers. Okay, but I am going to draw these for you. You will be given them, so you can check how they're drawn and then do the calculations. Or if you're feeling very confident, you can draw them yourself and then check back for the answers. Okay, so I've drawn out the structures for you for 13 to 16. Now that I've drawn out everything, you should be able to count all of the bonds that you're breaking on the left-hand side, see what you're making on the right-hand side, and calculate the overall energy change for each reaction. I've already given you the answers, but you need to make sure that you can get those answers yourself. You're using the values in the table in your booklet that we used for previous questions, and please take note of the big numbers that you are using to balance the equations. Pause at this point, work out the answers for yourself, and then press play when you're done. If you've got any of the questions wrong, I'm going to go through the answers here. So this is question 13. I've got hydrogen and chlorine, which means I've got 1 hydrogen-hydrogen bond to break, 1 chlorine-chlorine bond to break, gives me a total energy value of 679. For my bonds made, I've got 2 molecules of HCl, which means I'm making 2 HCl bonds. That gives me 864. Overall change is going to be 679, my reactants, minus my products, gives me minus 185 kilojoules for energy. Because it's a minus value, it's an exothermic reaction. In 14, if I look at the bonds broken, I've got 1, 2, 3, 4 carbon-hydrogen bonds to break. And I've got 2 molecules of oxygen, which means I've got 2 oxygen double bond oxygens to break. Taking those values from my table, I end up with a total energy of 2648. Looking at bonds made, I've got 2 carbon double bond oxygens, and I've got 2 molecules of water, meaning I've got 2 OH bonds in 1 molecule of water. I'm going to have 4 OH bonds into 2 molecules of water. Gives me a total energy of 3454. To calculate the energy change, it's my reactants minus my products. That gives me a value of minus 806 kilojoules of energy. Again, it's minus. Again, it is exo. If I look at question 15, bonds broken, I've got 1 carbon double bond carbon to break, and I've got 4 carbon hydrogen bonds to break. I've also got a hydrogen bond to break in my H2. Adding all that up, I get a value of 2702 for my reactants. Looking at my products, I've got a carbon-carbon bond to make, and I've got 6 carbon-hydrogen bonds to make. That gives me a total value of 2825. Reactants minus products gives me a value of minus 123. Again, another exothermic reaction. If I look at the last one, 16, if I look at all the bonds I need to break on my reactants, I've got a carbon-carbon bond to break. I have got 5 carbon-hydrogen bonds to break. I've got a carbon-oxygen bond to break, and I've got an oxygen-hydrogen bond to break. So to make sure I'm not missing any of those bonds, I'm going to count how many lines I've drawn. So 1, 2, 3, 4, 5, 6, 7, 8. Those 8 lines represent the 8 bonds. And then when I check here, 1, 2, 3, and 5 is 8. All of those bonds have been accounted for, and I get a total value of 3234. Looking at my products, I'm making a carbon double bond carbon. I'm making 4 carbon hydrogen bonds, and I'm making 2 oxygen hydrogen bonds. That gives me a total value of 3194. Overall energy change, reactants minus products, that gives me a value of plus 40. That means it's going to be an endothermic reaction. Okay, so when you're doing all these, you will have the molecules drawn for you. You will be given a table with all of the values. All you need to do is count the bonds that you are breaking, use the values in the table to get the total energy required to break bonds, count the bonds you are making, use the values in the table to calculate the total amount of energy required to make those bonds, then reactants minus products gives you your energy change. If you end up with a positive value, it's an endothermic reaction. A negative value will be an exothermic reaction.